All right. Properties of gases, the air we breathe. This is kind of a, sometimes when you study chemistry, you can't see the practical side of it. And it makes it tough to study, and kind of like, I get students all the time are like, that's what they like about my environmental chemistry class. All the chemistry we do applies to something you can relate to. Sometimes you're taking organic chemistry and you're learning about SM1 and SM2 reactions. You're like, what the heck am I doing this for? You're taking, quantum theory, and you're like, why am I worried about electrons? So gases are kind of nice, and that we relate to them. We've got an atmosphere filled with gas, right? We breathe in and out all the time. We've got, tires in our cars and our bikes and all of that, so we can relate to it. Master the ideal gas equation, derive all gas laws from that equation. So you're not going to memorize Boyle's law, Charles' law, Avogadro's law, the combined gas law, and all the other names and different ones and different iterations there are. There'll be a few that Dalton's law of partial pressure is the only one really you'll have to use mathematically that doesn't derive from the gas law. Graham's law of diffusion doesn't derive also, but I'm not requiring you to know that calculation-wise. That's why we skipped those first couple calculations in the chapter. Make sure you understand effusion, diffusion, the difference between those two. I think I even asked that in the quiz, possibly. Be able to interpret the kinetic molecular theory of gases, just understanding kind of that basis behind it, how different parameters affect gases, things like the way gases behave, what happens when you increase the temperature, the energy, all of that. Apply stoichiometry to reactions involving gases, and that's where you can take our stoichiometric knowledge and just do it the same way we did it before. A little bit of a nuance there, because one of the products or reactants might be a gas, and we'll be able to use PV equals nRT along with the stoichiometry. And then familiarize yourself with gas densities and gas mixtures, both qualitatively and quantitatively. The quantitative stuff can once again be derived from PV equals nRT, and that's the approach I'll take. So when you think about properties of gases, what types of things do you think about? You just blurt them out. You don't have to raise your hand. Temperature, pressure, volume, moles. Now you just give me PV equals nRT. Or how about like just some descriptive characteristics, things you can say about gases compared to solids or liquids or things like that, or how they behave. They spread out, right? They fill the volume of the container. So if we were able to evacuate this room and make it a vacuum, and then pump a really small amount of gas in here, theoretically, the idea is that it would fill the volume. Well, it's not going to fill. There's tons of space between the molecules, but they'll spread out completely, bounce off the walls, right? Where a liquid doesn't do that, you know that. And a solid just pretty much stays in place. If you were to pick one of these, there's a game when we were really young. I used to watch on TV or something. Which of these is not like the other? Something like that. So you know what the hell I'm talking about. The gas is the least like the solid and the liquid. It's the black sheep of the family, if you will. All right. Your solids and liquids, they have bonding going on, right? Liquids can slide past each other. That's why they're fluids. The bonds can be kind of like, release from one molecule and fold along each other and slide and rebond like that. That's what makes it flow, right? Solid, they're kind of rigid. All matter's in motion, right? The solids are doing this in place. Maybe not exactly that, but they're shimmying, right? That energy. They're not sitting there motionless. Okay, everything has motion. But the gases, they're the ones that they don't interact with each other at all. They're kind of snobs. They don't interact with the rest of the gas particles around there, And if they do interact, they bounce off each other, right? And they go about their way. The energy is conserved. You said these quick collisions are elastic. Okay, they change direction. This one might speed up. This one might slow down, but that total energy of that collision is elastic and kind of conserved that way. So they're kind of a little bit different than solids and gases. Than solids and liquids. So when you think about effusion, and I made this clear in the video, effusion through like escaping through a hole or a gap or something like that, right? Where diffusion is spreading out. I might have said this in the video. If you take food coloring and drop it into a beaker of water, it diffuses, and eventually the whole beaker of water will have that blue color if your food coloring is blue. That's diffusion. Okay, so gases diffuse, but also particles in solution diffuse. Effusion, your balloons, they're not perfect. They can have gaps in that mylar material or in the plastic material. And it shows this mathematically, and it's basically just a relationship. But basically, what you got to realize is the heavier the gas, right, the slower its rate of diffusion and diffusion. So we can say this all about diffusion and diffusion. There's a lot of information at the beginning of the chapter that distills down to the fact that something you already know. Typically, if it's bigger and bulkier, denser, it's going to be a little bit slower. Okay, and that's all this is. It happens to be inversely related to the square root, but we don't have to worry about that. We can just say, hey, as the density increases, the rate of diffusion will decrease. As the molar mass increases, the rate of diffusion or effusion will decrease. Because we're not doing any calculations with this. So as long as you understand that qualitatively, you're good. Here's the kinetic molecular theory, or KMT. Tiny volumes compared with the volume the gas occupies. So they're small, we call them kind of points with lots of space in between. Don't really interact much with each other. Collisions are elastic. The average kinetic energy of the molecules in a gas is proportional to the absolute temperature. One thing we'll have to realize in this chapter, you have to use Kelvin. Kelvin is the only scale that actually has, a molecular basis for it. Okay, so someone decided for Celsius, the boiling point of water will be 100 and the freezing point will be 0. And they had good reason, but it wasn't a molecular basis. Those scales are around long before we had a molecular basis or molecular understanding. Fahrenheit, same thing. They decided 212 and 32. Kelvin actually has a molecular basis. 0 Kelvin means 0 volume. Molecules stop moving, which is only a theoretical point because you can't get to that. You can't have a 0 volume if you have molecules. They would kind of like cease to exist. With the science fiction or something where the molecules would just, okay, you can't have that. You can't have a 0 volume. You can have no motion. So it's a theoretical temperature, but it's proportional and correlates with the behavior. So if I double the temperature, right, for a gas within a given cylinder, the pressure will double, but only if I double the Kelvin temperature, right? Not the Celsius or Fahrenheit temperature. That's what I'm trying to relay to you, that it is mathematically correlated directly with Kelvin, but not with the other temperatures. So your book talks about, where is it? The 3 different root means square. Heck, I was just looking at this the other day. Maybe it was. What was that? I saw that. Maybe was it in smart work? I don't think so. Anyway, what the heck? Okay. The average speed, the root means square, and I can't remember what the name of the other one is. There's 3 ways. There's actually a figure somewhere where they show it, I thought. I wasn't looking at another chemistry textbook. I don't know what I'm thinking of. I literally can't find it. Oh, there it is. It's figure 9.7. It's a little figure in the bottom right-hand corner, 399. The dashed line represents the most probable particle speed. The dotted line is the arithmetic average speed, and the solid line is the root mean square. There's 3 different ways that they're kind of measuring it, and they're important, but for us, we can talk about it qualitatively and say that basically any of those follow the same rule. There's a higher temperature, all of those inquiries, right? The lighter gases have a higher root mean square, average speed, all of that applies to all of those. So we don't need to distinguish between all three of them. And you can see here that the lightest gas, right, has the greatest, if you will, average speed, right? And it's got that distribution that takes some of these speeds way out to the right. Okay, it's some pretty fast speeds, but the heaviest one, O2, quite a bit back on the y-axis. So in general, it moves slower. And that shouldn't be surprising to you. The heavier, bulkier gases weight are going to be slower. This is just defining diffusion, the spreading of a substance through another. Okay. The average distance that a particle can travel through air or any gas before colliding with another one is called the mean free path of the particle. These are just some terminology that's used in gases. So the difference between diffusion and effusion, then again, is diffusion is slipping through a hole or a gap. Diffusion is spreading out. Tell me what atmospheric pressure is, what comes about. What is atmospheric pressure?
Use the example on the video, like when people go, or the football players and stuff go to a higher elevation, did they have more atmospheric or less atmospheric pressure?
Yes, they do. Why? So what is atmospheric pressure?
Have to, like, suck in the air.
Yeah, why?
Because the atmospheric pressure is the pull of gravity pulling the molecules.
Okay, so they're accelerating towards the Earth, right? Because Newton's laws tell us anything is attracted gravitationally. So why is pressure less at Mile High Stadium than it is at Titan Stadium? Less volume of particles, is that what you said? Okay, so meaning finish it. Why is the pressure less?
More space.
I mean, sheer number of particles is right? I mean, it is a column of air sitting on top of you. That's what the pressure is, right? So if you're up higher, you got a smaller volume of particles sitting on top of you, so your pressure is less. Okay, you've all kind of said things that are correct. You just need to piece it all together. Okay, so here it is right here. And this is a crude idea of a barometer. It wouldn't be a big open mercury trough like this, but you get the idea. It pushes down on the mercury, pushes it up the column. This has to be a vacuum. Otherwise, air would keep it from rising. And that would create a problem. Obviously, you wouldn't be measuring the pressure correctly. So it rises. We don't have a meter stick in here, but you'll know what a meter stick looks like. About 3/4 of that meter stick, 760 millimeters. I said that on the video, right? 760 millimeters. That's how high it rises. If we use mercury only, that's why we put the Hg there. We use mercury because of its density. I think I asked you that on the quiz. You can make a barometer out of lots of materials, but you'd have to have a room, big enough to hold it. You want something that's dense so that you can make an instrument that's a reasonable size, basically. You also don't want something volatilizing away too readily. I mean, mercury is volatile, but in a concealed container, it's not too bad. And it's going to stop when you reach, a kind of equilibrium of forces, a steady state of forces. Gravity wants to pull the mercury down, right? Gravity wants to push mercury, pull it back down. So you're going to balance of that is when you stop. So if I take this up to Mile High Stadium, that will start to drop that mercury because it's only about 0.83, I think, something like that. Instead of 1 atmosphere, this equals 1 atmosphere. That's another pressure unit. The other one I told you on the video is 760 torr. Okay, you need to be able to convert between those. We don't use Pascal that much in this course. It's like 0.83, so it's significantly different. So when I'm breathing, right, you breathe by pressure differentials, right? The air is pushed into your lungs as you control the volume with your diaphragm and everything, right? So if I increase the volume of my lungs, right, the pressure drops. They're inversely proportional, pressure and volume. That was part of the quiz. I increase the volume of my lungs, the pressure drops. The pressure differential between the air outside of my lungs now is greater. Air rushes in easily, right? And I exhale, I decrease the volume as my diaphragm changes, right? And now my pressure of my lungs is greater than the pressure outside and the air rushes out. Now, if I go up to Mile High Stadium, the difference between my lungs and the outside air is smaller. So that's the idea that you have to start working to get the air in. If you're not used to hiking at a high altitude or playing sports at a high altitude, you notice that. Questions about atmospheric pressure and how we measure it? And there it is there. Looks like I was close, about 0.83. This is one of the big problems with hiking high altitude. You go up Everest. I mean, obviously, no one does it without oxygen anymore. They used to do it without oxygen. Okay, so what I'm going to show you here is going to be brief but simple, hopefully. P equals nRT. What I want you to do is the one gas law you should memorize, take it with you if you will. You don't need, I don't mean for the exam, and just knowing this, everyone eventually knows P equals nRT. It just rolls off the tongue. Now, what you want to do is, when you look at these different parameters, we could have derived this equation because we just said that pressure and volume are inversely related, right? So if they're inversely related, they'll be the same side of a proportionality. Say that pressure, there's no symbol for inversely related, so we say pressure is proportional to 1 over the volume. That's the same way of saying inversely related, right? Okay. And you can do the same thing with moles, right? More moles, greater pressure, right? If I have a pump in more gases, right? Pressure is collisions with the wall, right? It's that force per unit area. So if you have more molecules, you have more collisions, you have more collisions with the wall, you have a greater pressure. So pressure is proportional to N. And as I increase the temperature, the pressure increases, right? If you take a can of aerosol, it's dangerous to have it in your car on a hot summer day. Proportional to temperature, right? So there's your equation effectively. What R does is allow you to switch from proportionalities to equals. It's just the non-scientific term, fudge factor. The scientific term is a constant. It makes all your units work out, right? If I'm doing a study with a bunch of cylinders and tubes, which is what some of the early work was, and I noticed, hey, you know, the volume's half. I mean, as I increase the pressure by putting weight on here, you can put a table here with weight on it. If I double the pressure, I half the volume. Well, I have to have a way to calculate the volume from pressure units, right? So that's the purpose of the constant R. It's going to allow you to be able to convert between units and get everything to work out in the right numbers. So you can measure this, and that's how you actually derive an equation. So ultimately, we get PV equals nRT from this proportionality. If it's inversely proportional, that's going to be on the same side of the equation. Because what that means is telling us if I increase the pressure, the volume has to decrease for this to stay the same. We're not changing anything else, right? Same numbers of molecules of gas at the same temperature. If I double the pressure, the volume has to be cut in half to get that double pressure. Or if you will, think of it like if I half the volume, my pressure will double. That's what these cylinders are showing you here. So that's how the gas laws came to be derived. They worked them individually, Boyle and Charles, right? When I reviewed this textbook, and me and someone else said the same thing, we think general chemistry textbooks should teach from PV equals nRT and show students it that way, but they all like to do it historically. Boyle did this, Charles did this, Avogadro did this. Ultimately, we have this, and that's the way it happened historically. But to me, a better way to learn it is to say, okay, now what you're going to do is anytime anything doesn't change in the problem or the question you're asked or the situation of the gases, you arrange them on the same side. Anything that's staying constant, you arrange on one side, okay? And the others, you put on the other side. Okay, so let's pretend we have a gas now at 1 atmosphere, and it's 1 liter. Okay? And we're going to increase the volume of that gas to 2 liters. And the question is, what's the new pressure? Right? So, N doesn't change, R is always a constant, and T doesn't change. So what you do is you say, my initial P, which was 1 atmosphere, my initial volume, this equals a constant. And since it's constant, it must equal my new volume and my new pressure. So you simply take the equation, put everything that isn't changing, that's constant on one side, everything that's changing on the other side, and now you can solve it very easily, right? You have 3 of the quantities. You have 1 atmosphere, 1 liter, and now you have 2 liters. This just goes away, right? It just becomes P1V1 equals P2V2, right? And that's easy. We doubled the volume, so our pressure, we doubled the volume, so we half our pressure. So we go to 0.5 atmospheres. So let's do one which, so that was Boyle's law. Okay, so here it is showing it geographically what happens, pressure, volume, and we get this asymptotic approach because obviously we can't get to 0 pressure and infinite volume, so we just keep going and going to you reach a point where we can't increase the pressure anymore. But here, 1 over V, you see that nice line proportional there to 1 over V. Let's do a practice and then we'll try some others, starting with P equals RT. A balloon is filled with carbon dioxide to a pressure of 1.5 atmospheres, 8.5 atmospheres, and has a volume of 1.54 liters. If the temperature remains constant, the assumption is obviously also the N is constant because it's the same balloon. So there's no more moles of gas, right? What is the final volume when the pressure is increased to 2.5 atmospheres? This should be a quick plug and chug. What'd you get? 1.14. Volume should decrease, right? Because the pressure is increasing. Think about it logically. So what we have is P1V1 equals P2V2, 1.85 atmospheres times 1.54 liters equals 2.50 atmospheres times V2. And you see the pressure is increasing. Make sure your volume is less. And Megan's answer seems reasonable. Anybody else confirm it? Megan confirmed it, so we're good. All right. Any questions? There it is, 1.14 liters. I confirm. Charles' law, now remember, in this case, it's volume and temperature that are changing. So all I'm going to do is rearrange everything. So I have V over T equals NR over P. Whoops. And NR over P is the constant. That's not changing. So now we replace that with V right here. V1T1 equals V2T2 because they both equal that constant. Okay, before and after, they both have to equal NR divided by P because N's the same, R's the same, and P's the same. That makes sense? And that's all. That's Charles' law. Now, you'll notice this doesn't go to 0. If you extrapolate this back, here it is. You'll notice the temperature is negative 273. And you'll notice the other thing here, it doesn't matter what gas it is, right? We're all going to extrapolate back to minus 273. That is 0 Kelvin, minus 273 Celsius, 0 Kelvin. That's why it's absolute temperature. It's the only one in which correlates with the absolute temperature of 0. where we're going to have a zero volume. Now you might say, well, wait, well, it's also zero. It's minus 273. What's the big deal? But the point is, it's not proportional, directly proportional. So if I double my temperature, I will double my volume. But the temperature doubled in Kelvin only, not in Celsius or Fahrenheit. Because remember, to get between those Fahrenheit, you've got to multiply by a factor, and then and then add, or add or subtract whichever direction we're going, 32. And for Celsius, you got to add or subtract that 273. Okay, so it can't be proportional. If it was just multiplied by something, we'd be fine, but it's not. So you have to use for all your calculations Kelvin anytime you're needed the temperature here. And we'll see that in thermodynamics too. All your temperature needs to be in Kelvin. It doesn't, I forget, this is from the book, because it doesn't say what the three different gases are, not that it matters, but they've got three lines. So. Plot of volume as a constant mass. Helium gas at constant pressure versus temperature. Each line represents a different gas pressure. Oh, I'm sorry, different gas pressure. It's the same gas, different gas pressures. But any gas will do the same thing. All right, then there's all these other laws. And some of them have scientist names and some don't. Okay, and there's Avogadro's. And then there's, I can never pronounce his name. Montan's law, which is not one that I actually learned. Then there's combined gas law, but there's some others you can even come up with. Like, let's see, we got Avogadro's volume and temperature. I'm sorry. Yeah. Wait, that's wrong. What is that? Oh, statement two ways, proportional. Either way, in terms of volume, I always learned in terms of obviously moles. So any combination of PV equals nRT, any relationship between any two of these besides R, you could apply the same way. They might not have a scientist names, whether it's P and V, P and N, P and T, T and N, T, whatever. We're going to take the same approach. We're simply going to take the equation, right? Put everything is changing on one side, and if four of them are changing, so be it. If three of them are changing, so be it. You'll have the data to be able to solve the problem. You'll need more data. And we can give them different names and things like that, but it all comes down to the same thing. Here's this one, which is a relationship with pressure and temperature, P1 over T1. So this derived from this. Knowing that pressure and temperature are the only two changing, so I simply bring the temperature over here, volume over there, and you have P1 over T1 equals P2 over T2. So whatever the problem you get on an exam or quiz or whatever you're challenged to solve in the future, start with PV equals nRT, put everything that's changing on one side of the equation and everything that's constant on the other, and then just simply say, initial and final, P1, P2, T1, T2, whatever, and solve it like that. Questions? So the combined gas law is just where we've got three of them that are changing: pressure, volume, and temperature. No different. We'll do one of those. A sample of oxygen gas is at 0.5 atmospheres and occupies the volume of 10 liters at 0 degrees C. What is the pressure of the gas if it is at 15 liters? If it is at, something messed up there. Something's missing or something. Well, anyway, it's going to be 25 degrees. Oh, no, that's right. That's fine. What is the pressure if now the gas has a volume of 15 liters and it's at 25 degrees C? The wording's a little messed up there. Something got deleted or messed up. So let's write P equals nRT. Do this for any problem. It doesn't matter, what you're solving. We can take this approach. Okay. and I'm going to look at this closely here. I'm going to say, okay, so there's a lot of information here. I've got a pressure equal to 0.5 atmospheres. I got a volume equal to 10 liters, and I got a temperature equal to 0 degrees C. But then I've got another volume equal to 15 liters and another temperature equal to 25 degrees C. So effectively, I got a V1 T1 and a V2 T2. And what is the pressure under this new condition? So basically what I'm after is P2. Okay, so the only thing that's constant then is N and R, right? So I can go ahead and say, okay, rearrange this and say PV over T is equal to NR. That's the constant, right? I now have the equation effectively saying P1 V1 over T1 equals P2 V2 over T2. See how I just grouped the ones that were changing together and the ones that were constants together, then set the ones that are changing equal to each other and using ones and twos. And now we can solve it. What is it? Maggie caught my mistake. I have to be in Kelvin. I'm seeing if she did that. Got to be in Kelvin. So we'll have 273 at the bottom rather than 0. And then what do we got? P2 is what we're after. 10 liters and 298K. So we have 0.5 times 10 times 298 divided by 273 divided by 10. And that should get us P2. What'd you get? Is that what you got? You should get that. So I didn't spend a lot of time with each individual gas law because I feel like it's somewhat tedious and redundant. Certainly read, because that's how you form your knowledge base of understanding some of the information that's related to you there about Boyle's and Charles' law and some of the experiments they did to figure it out with pressure and volume and all of that. So one of my people on my PhD committee said to me once, if you want to be a scholar, read everything across your desk. Read everything that comes across your desk. And I took that advice to heart. And reading is just becoming a lost art, but it's something we need to do, especially if you want to be a scholar, you want to be an expert in your field, you want to be, knowledgeable about stuff. You've got to just read. You got to make sure your sources are sound. There's too much mis and disinformation out there right now. It's what comes with the information age. It's good and bad, Heck, when I was doing my graduate work, that's when the internet was first coming out. You had to do an interlibrary loan. Sometimes I had to wait like a week to get a friggin' article I needed for my research. Now it's like, boom, go online and request it, and I have it like in my inbox the next day. Or trudging over to the library to grab a bunch of books and things like that. So much is available online, which is a good thing, but you got to be careful what you're getting into and what you're looking at. Okay, so everything we've been talking about is for ideal gases, which means they behave the way we've said. They don't interact much, right? They bounce off each other, all of this. Real gases at the end of the chapter, I don't cover that. I've never covered it in 20-something years of teaching this class. I don't know too many faculty that do cover it. It's just those situations in which you have gases, that are not behaving ideally. And usually they're extreme conditions. If the gas is super dense. You've got a bunch packed into a small space with a high pressure. Then they start to interact with each other, right? Super high temperature, things like that. In most cases, we don't have to worry about that. You're dealing with, high energy physics maybe and things like this. But for the most part, gases are going to behave ideally for us. And these are a couple of things that come out of that kinetic molecular theory. And that's the value of the universal gas constant, R. We haven't actually used it yet because it's not needed. We haven't needed to do these calculations. You don't need R. It's part of the constant. You don't worry about it. But if you're just doing a straightforward calculation of a gas that's not changing, then you need R. So those are the units. And effectively, there's your ideal gas equation, the units. So you always get a constant, right? On any exam you get. So if you forget the gas law, it's right there. R is equal to, liters is a volume, atmosphere is a pressure, moles and temperature. There's the ideal gas equation. It's in your units, right? It has to be. So anytime you have a constant, the units of the constant can help you solve a problem. So we also have to define standard conditions, standard temperature and pressure. And for gases, it's 0 C in 1 atmosphere. So for some of the thermodynamic stuff, it's 25 degrees C. So I can never keep it straight. But 0 C, 1 atmosphere. And 1 mole of gas at STP will occupy 22.4 liters. We don't use bar much. Will occupy 22.4 liters. Doesn't matter what the gas is. That's one of the keys to the ideal gas law. So it doesn't matter whether it's methane or hydrogen or nitrogen. It doesn't matter because they're small compared to the volume. So they behave ideally. Doesn't matter how big the molecule is. It really doesn't affect it because the gas has got so much space. So that's, if you actually remember that, it can become useful that it's 22.4 liters. You can calculate that to convince yourself. Take 273, 0 Kelvin, 1 atmosphere, and 1 mole, and use R and calculate V. That's all it is. And you'll get 22.4, right? That's all this is telling you. So once again, there's nothing in PV equals nRT that tells you the identity of the gas. So it shouldn't be surprising that it doesn't matter what the gas is. So let's practice using the ideal gas law. But I've thrown a little caveat in there. Instead of a straightforward calculation, which I think doesn't teach you anything. You can see that in the book. It's pretty straightforward. PV equals nRT. Just plug it in, right? I'm going to ask you to calculate the molar mass. Make you think a little bit. So, experiment shows I got 0.281 gram sample of an unknown gas that occupies 127 mils at 98 degrees C and 754 torr pressure. Calculate the molar mass. Not only that, I'm asking you to convert all of your parameters into the appropriate units. So let's do this as a class because there's a lot here. Someone just raise your hand and tell me one thing you want to do right off the bat. Okay, so someone do that for me. 90. Well, it's going to be just 271, right? I mean, 371 because it's just 2 minus 98. So we got to go temperature is equal to 98 degrees C plus 273. That gives us 371 Kelvin, right? What else do we need to do? Milliliters to liters. So the volume is 127 milliliters. And just move it 3 places. 0.127 liters. Divide by 1,000, right? What else? Torrs to atmosphere. So my pressure is equal to 754 torr times 760 torr per 1 atmosphere. Someone do that for me. Thank you. So, and obviously we're going to be using PV equals nRT, and R is equal to 0.0821, close enough, right? Liter atmosphere per mole Kelvin. Okay, so, well, I'm not sure how I'm going to get molar mass, but let's not worry about that yet, because I've got a temperature, a volume, and pressure. I can certainly get moles, right? Let's do that, and then we'll stop and think about it. So I need someone to calculate moles for me. So we've got, whoa. Oh, there's the work right there. There's a page to work on anyway. Need someone to calculate moles for me. It's going to be PV over RT, which, what was my pressure? 0.9921. My temperature, 371. Anybody? Double check my units. Atmospheres cancel out. Liters cancel out. Kelvin cancels out. I wind up with 1 over moles, which is going to be moles. So I'm good with my equation. My units will work out. 1 over n will give me n. Or 1 over moles, not really. Nobody yet?
I got 0.0041.
That? You got it also? Hersher confirmed it, so we'll go with that. 0.0041 moles. Any questions on how we got that? What do I do now? Right. I mean, molar mass is grams per mole. I gave you that hint. So we were given a mass to start with. So Houston's exactly right. We're just going to take 0.281 grams divided by 0.0041 moles. And we get 68 grams per mole. In some cases, you can actually figure out the identity of the gas because some of them have that unique molar mass that no other gas has. At least no other common gas. Like carbon dioxide's 44, hydrogen's 2, helium's 4, oxygen's 32. There's just common molar masses of gases to help you identify. So you get a smart work question or it asks you the identity of the gas, it'll be one of these molar masses that's kind of real common. And easy. Nitrogen's 28, 14 and 14. Of course, there's always organic gases that can have some of the same molar masses, but if you know it's just a simple gas in the atmosphere or something like that, you don't have to worry about that. Questions on this problem? Doing on time. Time flies when you're having fun. All right, densities of gases. Now there's a bunch of equations on here and it looks pretty intimidating. And once again, I don't care for this approach that much. I like to just think about it in terms of PV equals nRT and think about it logically. So when you think about density, how do you define density? You don't say to me, well, how do you define density? I was about to say, don't say mass divided by volume. Amount of material over a volume of substance, right? Yes, it's mass divided by volume. But when you think about it logically, it's the amount of material in a given volume, right? So if I have this, how might you arrange that to at least approximate density? How would you rearrange that and solve that equation so that on one side is something that would help us approximate density? What's that? Moles over volume. It's the only thing you have there that's going to be amount of substance, right? So effectively, N over V equals P over RT, right? And then you can actually substitute in molar mass and moles and all this. This is what gets confusing to me. So I don't worry about that. If I get a density problem, which we're going to do, I'm going to solve for N over V. Then I'm going to look at my units and do another step with other information I've given that's going to give me mass per unit volume, which is what density is. Instead of looking at this and saying, this is what all the books do, and it's like, this to me makes it unnecessarily complicated. Then you, rather than just thinking about it logically of all these equations here, and it's like N and N over V, and it's throw in the molar mass, and it's, if it works for you, great. But I'm going to do it like this. Okay, we're going to do an equation here. Second, there it is. Well, this one I've given you the density. I asked for molar mass. So when you do a problem like this, if you're asked for the density, you're going to have moles per liter, right? And ultimately, you want to get the mass per liter. So they have to give you, right, the molar mass of the gas to get the density. And you'll have, let's say it's 5 grams per mole, the molar mass, right? Well, if I multiply N over V times that, so effectively N over V times the molar mass is equal to density. You see? That's all you need. You just need the molar mass to get from the ideal gas equation to the density of the gas. And if you have the density, then just work back. That's why I always try to stress units. Look at the units, figure out what it is you have and where you want to get to. Take the information you have and manipulate that so that the units work out for you. So let's take a look. We'll do this first, then we'll take a look at this problem that I have, and then we'll go from there and see how you feel. This is just to explain a little bit of the importance of densities of gas. Buoyancy depends on densities of gases. So when I flew out to New Mexico, it wasn't for stinking United Airlines. I would have been at the Albuquerque Balloon Festival taking pictures. But instead, I was delayed in Houston. And I got there only for the night thing, and the wind was too much, and they don't do much at night. They just light up the balloons. But it's the largest hot air balloon festival in the world, and goes on for an entire week. And I met some people there and everything. They were showing me the pictures and everything. So not quite the same, but anyway, it's like hundreds of balloons all at once ascend, and they start like real early in the morning. They're all these hot air balloons. It's just gorgeous looking. But why do these balloons rise? Well, because the density of the gas in that balloon has to be less than the surrounding density. And the surrounding density, for the most part, is nitrogen, which is 78% of all the gas, and oxygen, which is 21%. So nitrogen is 1.19, helium is 0.169. So that huge difference in density is going to allow that balloon to rise. And those are at a particular temperature and pressure, obviously. And the temperature tells us that Charles' law tells us that, as the temperature increases, the gas spreads out more, the density decreases, right? So if you want to go higher, you can raise the temperature, use more heat, right? When you want to come down, you would cool that, you start to descend, right? All based on buoyancy, differences in the densities of the gases. Question? All right, so I've done a density one, but I've mixed it in to make it a little bit more involved here. So not only do I have to write an equation and think about this, I don't know if you've done something like this in the lab. This is a classic like carbonates. And when anytime you see a carbonate like this, that's sodium bicarbonate, that's baking soda, basically. And baking soda bubbles if you put it with like acetic acid, vinegar, right? Bubbling. What's the gas produce? Right, just see that right there and realize, oh, it's probably got to be carbon dioxide, right? So, did you do it? You don't do anything like this in lab. Did you do something like this in lab or no? You did? I can't keep track because you got all new labs and I haven't taught it yet. I'm going to ask to try to teach you because I would like to be able to do the labs and know what you guys are doing. All right. So let's see. HNO3 plus NaCO3, HCO3 yields H2O plus CO2. That's my carbonic acid, right? So what do we have left? We got the sodium nitrate, which is just going to be ions, of course, but we can write it as sodium nitrate. Nitrate power, two hydrogens, 3. So we're balanced, right? We're good. Yeah. So it's already balanced. You have to balance it. So the idea is you don't even really need to do this since it doesn't need to be balanced. We like to know it's 1-to-1, of course. But if you couldn't do this and you knew the gas was CO2, that's why I do one like this. It doesn't even need to be balanced. So it's a 1-to-1 relationship. All right. Gas density is given. Okay, so what is the molar mass and identity of the gas? Actually, we don't need to do any of this. I was thinking this is stoichiometry, but it's not. Sorry. There's no amount of material given. We'll do that a little bit later. So all we need to know is this gas, and we don't need to know it because that's what the question's asking. So we've got a pressure, 1 atmosphere. We've got a temperature equal to 23 degrees C, plus 273. That gives me what, 300 Kelvin? No, 296, thanks. .296 Kelvin. So we don't need to do any of that. We don't need to write the equation. We don't need to know the identity of the gas up front. All right, what else we got? We got a density too. So molar mass, we need to calculate the number of moles, right? But we don't have a volume either. So we can do N over V equals P over RT. I need someone to do that for me. I have the, no, I didn't have a blank sheet. Anybody do that? No one's doing. What is it? And that's moles per liter. Okay, now we have the density and we need to get the molar mass. So you need grams per mole, right? Should have had a blank slide here. It's getting kind of crowded. So we need grams per mole, and we have moles per liter, and we have grams per liter. Okay, so that's easy enough. So we need grams per mole. We need grams in the numerator. So we've got 1.83. I'm trying to find a place to write here. I'm gonna do it over here. 1.83 grams per liter times, and I need to get 2 grams per mole. So I'm going to get rid of the liters. So I'm going to say 0.041 moles per liter, right? That's going to give me the grams per mole, which is the molar mass. And it should be about 44 because we know the gas already is CO2. See how I just looked at the units and said, okay, let's solve for what I can solve for N over V. I don't have N, I don't have V, but that's going to get me moles per liter. And then I have grams per liter. So between the two of those, did we get 44? Did someone do it? Yes. Okay. 44 grams per mole. So we've got CO2. So if you try to memorize equations or think about what equation to use, it gets confusing. But if you look at the units and just say, okay, well, I can solve for N over V, right? I don't have N or V, but if I solve for that, I'll have moles per liter. And then I got another piece of information here that gives me grams per liter. So I can use that to get myself to molar mass, which is grams per mole. If you like it better just looking at all those equations and memorizing and that works for you, then that's what you have to go with. Questions? Okay. We good? All right. Gases in chemical reactions is kind of what I felt we were starting to do. In a chemical reaction involving a gas as either reactant or product, the quantity of the gas in moles can be determined from the ideal gas law if we know the volume of the gas and the temperature and pressure at which the reaction proceeds. So this is a classic combustion type reaction with CO2 and water being produced. Let's do one related to the airbag, because this is pretty impressive chemistry. You're talking about filling an airbag in a fraction of a second, something like nanoseconds, something like 50 to 60 liters after the car is impacted. Okay, that's how fast it has to happen, right? As soon as that impact happens, you have to inflate a balloon that's got about 50 to 60 liters instantly. So an automobile airbag inflate during a crash or sudden stop by the rapid generation of N2 from sodium azide, and the equation balanced is given to you. The question is, how many grams of sodium azide do we need to put in that mechanism so we make sure we get enough inflation of the airbag? And then I give you the dimensions of the airbag, the pressure, and the temperature. What do you want to do? So ultimately, we want to know how many grams of this, right? And this is the information we have, right? So I can always use that molar relationship, right? If I figure out how many moles of N2 I need to fill that bag, then I can use stoichiometry to say, okay, well, I need 2 moles of sodium azide. I can use the molar mass of sodium azide to get to the grams of sodium azide, and that's what the question is. So how do I get the moles of nitrogen gas? Well, we can use PV equals nRT, right? We can give it a temperature, a pressure. That's the way you have to look at this problem. Okay, so N is what I'm after. I've always got R, I've got a T, I got a P. The volume's what I need, and there I've got dimensions. So Someone do 48 times 48 times 25 for me. What is it?
57,600.
Units are going to be what? Cubic centimeters, which is equal to a milliliter, right? So we've got to convert that to liters. So we've got 57.6 liters, 100,000. 57.6 liters. We now have the volume. Okay, so we did 48 times 25. And each of those are centimeters, 48 centimeters by 48 centimeters by 25 centimeters. So you got cubic centimeters, which is a milliliter. So we just convert to liters, divide by 1,000. Now we have a volume. So we can calculate N, and then we can use stoichiometry, right? That's where we're going with this. All right. P equals nRT, rearranged. .2 atmospheres, 57.6 liters, 0.0821 liter atmospheres per mole Kelvin, 288 K. Just double checking again, I did this right. 1 over moles again, good to go. Equals, how many moles do I get? What is it? 2.92. 2.92 moles. Now the equation's right there for us. We can use our stoichiometry. It's just a long problem. But you can have two separate problems on an exam. I can actually just calculate the moles, or I can actually give you that and figure it out stoichiometrically. 2.92 moles. What is that I calculated? 2.92 moles of what? N2. Not a bad idea to write that. N2 times, we're after sodium azide, which is there. So we're going to say 2 moles of the sodium azide for every 3 moles of N2. So my moles of N2 is canceling out. I'm at moles of sodium azide, which is what I want. Times, and we don't have, I didn't give you the molar mass, did I? So we have to add it up. 3 times, that's pretty easy. 3 times 14 plus like 23 for sodium. $65 or so. $66 grams per mole, right? 66 grams per mole gives me what? 120, and I had 127 down here. $127 grams. So it brings a lot with it. I mean, a lot of what you've learned, the stoichiometry, the ideal gas equation. Questions on that one? Did you get something different? Yeah, there might be a rounding error somewhere. I think Houston got 126 something. 288.0821, 57.6, 1.2. And maybe if you didn't round this here, something like that, you left it in your calculator, you might get a slightly different answer. Everybody understands how we did it? Okay. Mixtures of gases. So this is Dalton's law. This is the one you can't get from the ideal gas equation. All gases behave independently of one another. So if I got a mixture of gases, effectively, if I have a total pressure, the individual gases contribute part of that pressure based on their mole fraction or their percentage, the amount that they are present in that gas. And so we can define a mole fraction, which is no different than angular fractions. So whatever the particular gas is, the number of moles of that gas over the total number of moles, or you can do it in terms of pressure too. The individual pressure divided by the total pressure, something like that, you get this fractional component of the gas. So the easiest way to show you this is to say, okay, the atmosphere, once again, 78% nitrogen and 21% oxygen, right? And if we use sea level, we say the total pressure of atmospheric gases is about 1 atmosphere, right? All Dalton's law of partial pressure is telling us is that, well, N2 represents 0.78 of that total, right? In decimal form. So it must be 0.78 atmospheres. So the pressure of nitrogen in the atmosphere will be 0.78 atmospheres. And the pressure of, and the pressure of oxygen will be 0.21 atmospheres. That's all Dalton's law of partial pressure says. You do it in percentages, mole fractions, but the pressure is directly proportional to the fraction of that gas within the mixture. So it's going to be a fraction of that mixture. It's going to be that same fractional portion of that pressure also. That's all it's saying. Forgot that I had that though. So. Question. Wow, we blew through that. It's because I don't go through all the individual gas laws. That takes a lot of time. So if you have any questions, certainly reach out. Kinetic molecular theory. Gas laws, density of gases, gases and reaction stoichiometry, gas mixtures, and fusion and diffusion. That was the beginning of the chapter.